Hello juniors, today we're going to continue working with binomial distribution. If you remember, binomial distribution is this formula over here in which we can calculate the probability of a binomial or of variables that are binomially distributed. Remember that the concept of binomially distributed is when a specific event can either have a success or a failure. It has only two different alternatives in the universe, either success or failure, such as, for example, tossing a coin, right? Tossing a coin has only two different possible outcomes, which are either getting head or getting tail. Okay, so last class we discussed this concept and we applied it to one example where we found the different probabilities given number of trials and the probability of success at each attempt, right? We calculated a probability of exactly 4 successes, at least 1 success, and finally 3 or fewer successes. And I showed you how to use a calculator to work with this type of problem, okay? So if you don't remember this clearly, I strongly suggest reviewing this tutorial video in order to understand this better. So what we're gonna do today, here you also have some instructions for using the calculator in this particular example. And today we're gonna keep on working with more examples about this. Okay, so I'm gonna be showing you how different problems of binomial distribution can be presented and how to solve them. You're gonna see that most of them are solved in the same way. It's just using the same formula, right? So it says for number 2, if the variable x is binomially distributed. Remember, this symbology means that variable x is binomially distributed with 6 trials and a probability of success of 1/3. Remember, the general form for that is x is binomially distributed with n trials and a probability of success p. It is always given this way, okay? So if we're given these numbers, you should already interpret that this first number corresponds to n, and the second number corresponds to the probability of success, okay? So find to 3 significant figures all of these different probabilities. Okay, so for part A, we want to calculate the probability of having exactly 2 successes, right? So first of all, we're gonna identify here our value of n, which we already should know, that is 6, and the value of p is equal to 1/3. Now, in this particular situation for part A, we are gonna say that x is equal to 2. That's what we want. We want to calculate the probability of x being exactly equal to 2. Let me bring the formula here for a second. I think I write it here, this one. Just for you to remember the different terms. There. Okay. So we want to calculate the probability of getting 2, right? So the value of r, remember, the value of r is the number of successes we want. In this case, r will be 2, okay? So this is the same as saying that r is equal to 2. Okay, and we have all of the rest. We already have p, we can know q, but we don't need to calculate q actually, because we can use our calculators directly. This is an exercise in which we are allowed to use calculator. So to calculate the probability of x being equal to 2, we need to use our calculator. If you remember the steps, okay, so if you look at the calculator, remember the steps. We go to menu statistics, which is menu 2. We don't need to plug in anything in list 1 and list 2. We're just going to go to dist for distribution and then binomial, right? Because this is a binomial distribution. We click on binomial. And now, since we want to find the probability of exactly 2 successes, then I'm going to click on BPD. Remember that whenever we have exactly 2, I'm going to write that here. Exactly. We use BPD, which is the binomial probability distribution. So we're going to click on BPD f1, and here we need to plug in the values. The value of x is the value of r, in this case should be 2, we want exactly 2 successes. Number of trials is 6, and the probability of success is 1/3, so 1 divided by 3, and we get that probability. So you go to execute, and there you have the probability of exactly 2 successes. So probability of x being exactly equal to 2 is equal to 0.329. We're going to leave it to 3 significant figures as we're asked. Okay, so this is the result for the first part. Okay, so then we're asked to find for part B, it says find the probability of x being less than 2. Now it's where it gets a little bit more interesting. It's a probability of x being less than 2. X being less than 2 means that we need to calculate the probability of 0 successes plus the probability of 1 success. Those are all the alternatives for x being less than 2, right? But instead of calculating this independently, because we can calculate this separately and then add the two values using BPD, we can do this directly by using, I'm going to write it like this, less than. Whenever you see less than or more than, you should automatically think about using BCD in the calculator, which means binomial cumulative frequency, right? So if we write the information again, we have the same information. N is 6, the probability is 1/3, and x should be 2, okay? So let me show you the calculator once again. If we go back, let's go back. We're going to go to dist binomial, but instead of clicking BPD, now we're going to click on BCD because we want we want x to be less than 2, okay? So in lower, one thing I told you last class, which is not necessary, is that you don't need to write a very small number here. You can just write as lower 0, and as the upper, you're going to write 2, which is our upper boundary, right? Sorry, not 2, 1. Because we're going from 0 to 1 only. Number of trials is 6, and the probability of success is 0.3333. So that's fine. So you click on execute, and there you have the value. So I'm going to write this. Probability of x being less than 2 is equal to 0.351. This is correct to 3 significant figures. Okay? You can try, if you want, to calculate each of this independently, and then add them both, and you'll see that you're going to get the same result. Okay, then for part C, it says probability, write this a little bit lower. It says probability of x being less or equal than 2. Okay, so now the difference is that we're just adding probability of 2, right? This is probability of 0 plus probability of 1 plus probability of 2. So we're doing exactly the same thing, the same steps. I'm just going to write this here, probability of x being less or equal than 2. But the only thing that changes is that now we need to put as the upper boundary, we need to put x equals 2, right? So if I show you that again, we're going to go back. And instead of writing upper at 1, it's going to be upper 2, right? Because we're now including the value 2. You go to execute, and that's the value, 0.680. So the probability of this particular event of getting less or equal than 2 successes in this particular event is 0.680 or 68%, right? Okay. Finally, for part D, it says find the probability of x being greater or equal than 2. Probability of x being greater or equal than 2. Okay. For this particular part, the use of the calculator depends on the model of the calculator you have. In the older models, the only way that you can solve this is by thinking the other way around. The probability of x being greater or equal than 2 is the same as saying 1 minus the probability of x being less than 2, right? Because probability of, let me write that down first. probability of x being greater or equal than 2 is like saying probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability of 6, right? But you're not going to be calculating all of this independently because you're going to waste too much time. So you should see that this is the same as saying 1 minus the probability of x being less than 2, right? X being either 0 or 1. It's the same thing as saying this. So it's actually easier to calculate only this and then subtract 1 minus that, okay? And actually we have already calculated this value, which is this one over here. So the probability of x being greater or equal than 2 is 1 minus 0.351. And 1 minus 0.351 is 0.649. 0.649. So this is a probability of x being greater or equal than 2. If you have a calculator similar to mine, let me show you what you're going to do in that case, or what you could do in that case. If we go to a calculator, you go back, and in the lower, we're going to write 2, right, which is the lower boundary, and the upper would be 6, right? We go from 2 to 6. And then you calculate on execute, and there you get the same value, right? 0.649, if we round it to 3 significant figures, okay? Super. So that's it for this example. This example was for you to understand how to use calculator in order to solve these problems, okay? Now let's move on to this example. This is a more real-life application, right? It says the probability that I get a bus to work on any morning is 0.4. What is the probability that in a working week of 5 days I will get a bus only twice? Okay, so let's identify first of all our information. The first thing we have is a probability, right? The probability that I get to a bus. So we're gonna call that the probability of success. So P, the probability of success, is 0.4. Remember the elements of the formula. I'm gonna copy this again. Probability of success, P is 0.4. Then, what is the probability that in a working week of 5 days? What is this telling us? 5 days is the number of trials, right? We have 5 days in the week, right? And out of those 5 days, I want to get on a bus only twice, it says. That means that our value of R, which is how many successes we want, would be equal to 2. Okay, remember the value of R is the same as the value of X in the calculator. So R is equal to 2. So basically, if we read the question again, what is the probability that in a working week of 5 days I will get on a bus only twice? Only twice means exactly 2 times, right? So what I want to find here is the probability of X being equal to 2, right? So that's exactly what I'm going to do. And I'm going to use GDC. Using GDC, we're going to calculate using BPD, right? Because it's exactly 2, and we're going to calculate that value. So if we go to the calculator, we're going to go back. We're going to go to dist, binomial, and BPD again. Now the value of X is 2, the value of number of trials is 5, and the probability is 0.4. So we click on execute, and there we have the value. So the probability of X being exactly equal to 2 is equal to 0.3456. We can write the exact value in this case because it's a finite decimal number. Okay, so that's it for this exercise. Now let's move on to the next exercise. This example, it says, when administering a drug, it was known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What is the probability that all 10 patients were cured in both groups? Okay, so let's identify first of all our information. The probability of success of this drug is 0.8. Remember, you should always write the probability in using decimal numbers, not using percentages. So probability of success, 0.8. Then it says it was administered to 2 groups of 10 patients. So I'm going to show you 2 ways to solve this problem. The first one, which is more logical for me, is to only consider first 10 patients. So n, the number of trials, because I administered this to 10 people, and for each time I administer the drug to someone, it has 80% of success, right? So number of trials would be 10, right? I try this 10 times with 10 different people. So what is the probability that all 10 patients were cured in both groups? If I want all patients to be cured, then my value of R, which is my value of X in the calculator, should be equal to 10 as well, right? We want all of them to be cured. So I need to calculate the probability of X being equal to 10, right? Exactly 10. So again, we're going to be using BPD in the calculator. So using GDC, BPD, because it's exactly 10, and we're going to calculate this probability. The probability of X being exactly equal to 10 is equal to, and you already know this part. I'm going to calculate this. We're going to go back. This is BPD. So X is equal to 10. Number of trials is also equal to 10. And the probability of success is 0.8. You calculate this, and that's the value, 0.107. So you see that the probability that all of them get cured is actually very small. This is 10.7%, right? Although the drug has 80% of success. Okay, so that's pretty interesting. But now, this is the probability of only one group getting all 10 patients recovered. If I want, I'm going to write the whole value here because we're going to need the whole thing. If we want both groups to have all of their patients cured, then we're going to say the following. We're going to say that the probability of getting X equals 10 in both groups, is equal to, this is the probability of getting 10 patients cured in one group. So if I want to find it in 2 groups, then I need to multiply this probability twice, right? It's the probability of one group getting cured entirely times the probability of the other group getting cured entirely, right? Which is exactly the same value. So we need to multiply these two, and we're going to get the final result. If you do this in the calculator, you should get 0.0115. So you see that the probability of all 20 of them getting cured is very, very small. It's 1.15% only, okay? Now, there's another way, if you want to consider this, although I don't really like this way, but it's kind of faster, is the following. If you consider it to all of this to be only one group, 2 groups of 10, we're going to join them and consider them to be one group of 20, right? So if we do that, we're going to say that the probability of success is 0.8 as always. N is now 20. And if we want all of them to be cured, R should be equal to 20. And if you calculate this in the calculator, probability of X being equal to 20, you're going to see, let me show you. If you go back, we're going to change X is equal to 20, number of trials 20, success 0.8, and you see that you get exactly the same value, 0.0115. So this is another way of calculating the probability, considering the 2 groups as one. Okay, now let's move on to this last example. Let me check this a little bit up. Here. So, let me see. For this last example, it says, a box contains a large number of carnations, of which 1/4 are red, the rest are white. Carnations are picked at random from the box. How many flowers must be picked so that the probability that there is at least one red carnation among them is greater than 0.95? Okay, this is an interesting problem because it already gives us the probability, right? But we now want to find the number of flowers that must be picked in order to get this probability. So things change here a little bit. Let's write our information first. Our objective is to get red carnation, right? So the probability of success for red carnation is 1/4, it says, right? So we're going to write this. The probability is equal to 1/4, right? 1/4. That means that the value of Q, which is the probability of failure, would be 1 minus 1/4, which is 3/4. Okay? So, let me write the information here. We know that the probability of getting at least one red carnation, must be a value which should be greater or equal than 0.95. That's what we want, right? Now, let's think about what this means. The probability of getting at least one red carnation. If you think about that, the probability of getting at least one red carnation is the same as saying 1 minus the probability of getting 0 red carnations, right? So this sounds a little bit more easy to calculate, right? We know that the probability of getting at least one red carnation must be 0.95, must be a value which should be greater or equal than 0.95. So this is the probability of getting at least one red carnation. And we know that getting at least one red carnation is the same as saying 1 minus the probability of getting 0 red carnations. So here we have an equation, well, actually in this case it's an inequality, where we can find how many red carnations we need to, how many flowers must be picked in order to get at least a probability of 0.95 to get at least one red carnation, okay? So let's write this information down. We know how to calculate probability of 0. If you remember, and I'm going to bring the formula back again, from this formula, we know that, let me put it here. We know that in order to calculate probability of 0, let me write this as 0.95 less or equal than 1 minus, and probability of 0 is the same as saying the probability of success to the power of 0 times the probability of failure to the power of n. We're taking n flowers. We still do not know the value of n. We're going to calculate that. But the probability of getting 0 red carnations is this, right? Probability of red carnation to the power of 0 times probability of not red carnation to the power of n. And this value of the combinations, whenever you have something n and 0, whenever the value of r is 0, then the combination is always equal to 1. Okay, that's why we do not consider that here, because the value is just 1. Okay, so you see that we can solve this, right? We know that any number to the power of 0 is 1, right? So let me write this down. This is all equal to 1. So 0.95 must be less or equal than 1 minus, and this is 3/4 to the power of n. Okay? And now I need to solve for n. You see that my only variable here is n, right? So if I take this, for example, to the left side and I bring this to the right side, we're going to get that 3/4 to the power of n must be less or equal than 1 minus 0.95. And if we calculate this, this is 3/4 to the power of n, and this is less or equal than 0.05. Now, if we have our variable that we want to solve for in the exponent, we need to apply something that we have just learned in math, right? Applying logarithms, okay? We need to apply log. This is if we want to solve this manually. Then I'm going to show you other alternatives to solve for this, but you're going to see it's the same, okay? So if we apply log, we're going to say that this is n, we can take the exponent down, this one, we can bring it to the front, n times logarithm of 3/4 must be less or equal than logarithm of 0.05. Okay, and there we have the solution, right? N must be less or equal than log of 0.05 divided by log of 3/4. And if we solve this using calculator, you're going to get that n is less or equal than, and we get 10.4, which means, I think I made a mistake. Yes, there's something that we need to consider here. If you calculate the logarithm of 3/4, the logarithm of 3/4 is a negative number, okay? Let me write this. Log of 3/4 is a negative number. If you do this in the calculator, you will see that. It's a negative number. That means that whenever we divide an inequality by a negative number, remember we need to flip the signs, okay? I already taught you this. So this should actually flip sign. It should become greater or equal, greater or equal, okay? So I'm going to write that here. Inequality flips sign. Okay, so we get that n should be a value greater or equal than 10.4. But since we're talking about flowers, it cannot be a decimal number, right? So that means that n should be at least equal to 11 flowers. And this is the solution to our problem. We need to take at least 11 flowers in order for the probability of getting a red carnation, in order to get a probability of getting a red carnation which is greater or equal than 0.95, okay? So this was a very interesting problem. You can also solve this, instead of doing all of the logarithm and all that, you can just solve this using graph in the calculator, okay? We just need, let me see, this expression over here in order to solve this. Let me show you this quickly, just for you to understand this. So if we go to the calculator, here, we're going to go back. We're going to go to, we should actually go to menu graph, menu 5. I'm going to erase this. And for the first function, you're going to put what we have on the left side, which is 0.95. So 0.95. And on the other side, you're going to put 1 minus 3/4 to the power of n. Okay, so we're going to put 1 minus and 3/4 to the power of n, or to the power of x in this case, when we put it in the calculator, right? So if we draw this, let's draw, and there you have the two functions, right? And we're going to find the intersection point. If we go to Shift G solve intersect, you're going to see that they intersect at exactly 10.4, right? That means that in order to have a probability greater than the blue line, then this value of x should be the first integer number, which is greater than 10.4, which is 11, okay? So that's how you solve this problem using a calculator, okay? So I hope this was clear, juniors. If not, please let me know. We're going to clear these doubts in future live sessions. We're going to be practicing with lots of exercises about this as well. So I hope you're fine, and let me know if you have any doubts. See you.